Metering and Energy Storage for Power Distribution Systems by Nazanin Hushman and Dustin Wolesky.
Smart meters are a new technology used by power companies to communicate data between themselves and the consumers. This figure shows the architecture for BBS Access AMR solution. As it can be seen, smart meters use a two-way communication to send data and receive signals as well as commands. Processing is done to the data after the information has been transmitted through the Wide Area Network or WAN to the main collection station. The data is collected locally in 15-minute intervals by the meters and transmitted through Local Area Network or LAN to the substation. Smart meter transmission can be divided into two basic types: radio frequencies, which uses wireless communication, and power line courier, which uses power lines to transmit data. Benefits of smart meters. Efficiency. Smart meters preserve their accuracy throughout their entire life cycle of the product. The accuracy is due to the fact that the new technology is not affected by air or any particles in it. Also, since the consumers can access their electricity usage at any time, they can modify their electricity expenditure behavior and use their high-power consuming appliances during rough time of the day, therefore reducing their electrical bills. Another benefit of smart meters is their ability in recognizing power outages as well as the ability to detect any tampering with the meters. In either case, a signal will be sent to the supplier to ensure safety of the consumers. Finally, environmental protection. The old meters are 100% recyclable, which makes the transition easier. Moreover, the structure of the smart meters are built in such a way that will result in a reduction in greenhouse gas emissions. Inconveniences. The implementation of the new meters not only costs a lot for the providers due to the initial investment, the consumers are forced to pay an additional fee on their bills to cover the cost of putting in place the new process. Another main issue that is brought up frequently regarding the smart meter is privacy. There is a possibility of law implications since the data stored by the smart meters shows whether or not there is anyone at home. But as long as the suppliers are able to manage and store immense amount of data, keeping the information secure to protect their clients, customers should not worry. Health risks. Depending on the location of the meters, exposure to the electromagnetic field differs. The worst-case scenario is apartments that have collector meters. The building neighboring to the location of the meters will have significant health risks, but scientists have recommended in having pulse radio frequency at a threshold of 1 microwatt per centimeter squared at 10 feet in order to avoid any health issues associated with the meters. Implementation. The number of countries utilizing the change to smart meters is growing. Each country has decided to take on a different path in implementing the new equipment. Depending on the country that is the lead organization for smart meters, the level of consumers' input towards regulations may vary. The deployment of smart meters found its way through Europe, starting with Italy. However, in July 2009, following a regulation-driven rollout, Sweden became the first country to completely replace their existing meters with smart meters.
The existing power grid. Along with the deployment of smart meters, energy storage is a vital aspect to our sustainable power future. Energy storage is already important for the existing power distribution system and will become even more essential as our power grid becomes supplied with more and more sustainable power generation. It is through the incorporation of many different energy storage techniques that our current energy is being stored, and in the near future that will remain the case. This range of energy storage techniques is due to the limitations on the systems, whether that be the capacity of energy that can be stored, the terrain necessary for the storage, or the efficiency of the system itself. Current sustainable energy storage techniques put a strain on power grids due to their dynamic or static natures, and therefore, the coupling of these generation techniques with energy storage systems is necessary for sustainable power production in the future. Pumped hydro has been found to be an excellent method for energy storage where the terrain is available. Pumped hydro operates typically at a total efficiency of 70% and would be a great alternative to fossil fuels, but for the fact that it is only available in specific locations. Pumped hydro uses two lakes and a mountainous terrain to pump water from a lake at a lower level to a lake at a higher level, thus transferring the electrical energy into potential energy in the higher lake. Once this energy is needed, the water from the second lake will be allowed to flow through a turbine, converting that potential energy into electrical energy. Flywheels. Flywheels are a kinetic energy storage system that uses the rotation of a mass to absorb and release energy. This mass is known as the flywheel and is most often situated in a vacuum enclosure while being supported by low friction bearings or a magnetic suspension system. This is in order to reduce drag and maximize energy conservation. The energy that may be stored in a flywheel is limited to the tensile strength of the flywheel, which will be stressed by the force produced by the angular acceleration. This stress on the flywheel limits the system to relatively small amounts of energy storage, but due to the design of the device, it is able to absorb and distribute power with very little delay. Compressed air energy storage. The process of compressed air energy storage is the process of converting electrical energy into potential energy. Up till now, the main issues involving CAES have been the efficiency factor due to the loss of heat energy of the air as it is passed and stored in the cabin. Currently, RWE and General Electric have plans for the implementation of an adiabatic compressed air energy storage in Germany, where there will be two forms of storage. The first form of storage is the storage of the heat that results from the compression of the air. This heat will be stored as a separate component in an insulated tank that will be filled with heat exchanging stones. The second form of storage is the storage of the air itself. This will be stored in a salt cavern well below the Earth's surface. Once the energy is needed again, the air will be released from the cavern, mixed with the heat that has been stored, and fed through a turbine that will convert that stored energy back into electrical energy. This adiabatic process plans to increase efficiency up to 70%, which would then rival pumped hydro energy storage. Fuel cells. Currently, with fuel cells being limited to 50% efficiency, along with the transportation of the necessary fuel sources and the efficiency of the fuel creation itself, fuel cells are not a viable source for energy storage on the scale of large power distribution. Solid oxide fuel cells are a main way to transport energy using hydrogen. The results of current research have suggested that SOFC can produce power on the order of megawatts with net electrical efficiencies up to 70%. This efficiency has yet to be proven in a commercial application, and the methods for producing such results require additional considerations such as gas turbines and methods for recovery of any thermal losses. In addition to requiring extra components, SOFC operates in a temperature range from 700 to 1000 degrees Celsius, and thus requires specific material manufacturing techniques, not only for the reaction, but also for the equipment housing the reaction. Hydrogen production. As stated earlier, SOFC requires hydrogen as a fuel source, and thus the overall efficiency of an SOFC plant as a method for energy storage must also consider the production of hydrogen. Currently, over 90% of the world's hydrogen manufacturing is done by natural gas at an efficiency of approximately 80%. If we are to look at SOFC plants as a means of renewable energy storage, alternative methods for hydrogen production must be considered. The process of hydrogen production using nuclear reactors has yielded significant results as to a possible means for renewable hydrogen production. Using a high-temperature steam electrolysis method, nuclear energy can produce hydrogen at an efficiency of 90 to 95% at temperatures greater than 800 degrees Celsius. This high temperature causes strict requirements on the materials manufacturing process to construct such a facility, and therefore this technology is waiting for the development of large-scale, durable, high-temperature steam electrolysis units. Integrating high-temperature steam electrolysis and SOFC. The HTSC method is effectively the reverse process of SOFC, and would therefore create a very compatible system if both methods were integrated. If the two systems were successfully combined, the energy storage efficiency could be as high as 65%, disregarding any losses due to the transportation of the hydrogen. To avoid such transportation losses, it would be logical to assume that the HTSE plant and the SOFC plant could be located near the nuclear plant in order to conserve intersystem losses.
In conclusion, smart meters are an overall beneficial solution to sustainable power distribution systems. That being said, it is important that regulations are put in place to mitigate the health risks that result.
This sustainable power distribution system will require a variety of energy storage to deal with the uncontrollable dynamic and static characteristics of sustainable energy generation. In the future, methods such as hydrogen fuel cells may be a viable source to control these previously uncontrollable characteristics. Materials manufacturing will be a vital component if any such fuel cells are to be integrated into the system.
Thank you for watching, and please refer to these references for any information regarding the illustration.